Hi class, this video is going to help with 11.5, and what we're going to look at on this one is the absolute max and absolute minimum. Okay, so we've looked at the local max, local min, and those actually could be the absolute. So if I'm thinking about a parabola, right, then it is that the local min and local max is the absolute. But how would we know that? We have to check. And so that's what we're looking at. So an absolute max is where this whatever number, this one calls it C, is the highest point if it is above all other points in the domain, right? I mean, that's just, is it the highest point? Minimum, same thing. So if you want to pause and get that in your notes, you can, but really think through what is an absolute max? The highest point. Absolute min, lowest point. Do they always have an absolute max or an absolute min? No. So note that also. So let's look at this first little graph here I have in question 1. If we look at this, we have an absolute max at 2. So it's at the point 0, 2. So x is 2, x is 0, y is 2. And so our absolute max is what we have. Do we have an absolute minimum on this one? No, because those arrows go down forever and ever and ever, so they don't stop. They have to stop for us to have an absolute one. Okay, next one, absolute min on this one, right? So it's the other way, and it could be a V shape, it could be a U shape. There's lots of different options there, but this is an absolute min, right? And it happens at the point x is 2, y is -3. So we're looking at that y value to be the lowest, okay? We don't care what the x is. We just care where it is the lowest. Well, we do care, I mean, we have to use the x to find it, but basically we would get that 2 by a critical value, right? But then we're checking this number to see if it is the lowest. Here's one more from a graph. So notice this one goes on forever down and then whoop, 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 and up forever. This one does not have an absolute max or absolute min because we can't find the lowest point and we can't find the highest point. Do we have a local max and a local min? Yes. Local max, local min, but no absolute. All right, so those are my graph ones. So basically, when we do these problems, we are going to look for those critical values and we're going to look for endpoints. So we check critical values and endpoints and we see which one's the lowest or highest, and that will give you your absolute max or min. And if they don't exist, then you won't have one. But this is our extreme value theorem. Oops, let me just a little, there we go. An extreme value theorem says a function f that is continuous on a closed interval ab has both an absolute max and min. So of course it does. If I stop us, right, we can't go on forever, well, then we're going to have an absolute max and an absolute min. Okay, that's all that's saying. Here is the procedure for finding our absolute on a closed interval. Okay, not an open interval, closed interval. So basically, you're going to check if it's continuous from A to B. Okay, you're going to find your critical values. How do I find a critical value? Oh, I take the derivative, set it equal to 0, right? Or where the denominator equals 0. And if it's continuous or not, basically, do you have an asymptote in there? Do you have a hole in there? You evaluate then your endpoints and your critical values. And that way you find your largest, which is your absolute max, absolute min. Okay. So we're not, I mean, it is a new idea, but thank goodness we really aren't doing new algebra or anything like new mathematically. We're still looking at those the critical values, those local min, local max, are they the absolute? So we're still doing the derivative, set it equal to 0. You can even use the second derivative to see if it's concave up or down. But let's go ahead now and do a couple problems. And I pray this sound is working. I've only recorded all the videos for chapter 11 about 10 times to get one that's maybe okay. Okay, all right. And so let's look at, this is, it's not really our first problem, but we'll call it that. Okay, so I have x to the third plus 3x squared minus 9x minus 7. And it is only on the interval from -6 to 4. I don't want to go beyond that. So what are we, well, first of all, we know it's continuous because there isn't a 0 in the denominator to make a hole somewhere or make an asymptote. No square root to make it to where it's greater than some certain number or less than. There's no natural log where it can't be negative, so we're good. So first of all, we know it's continuous. And what we're going to do is we're going to find the derivative. Okay, so the derivative of this one's pretty easy. You're probably like, yes. So we just do our power rule. So we go 3x squared plus 6x minus 9. There's our derivative. And now we have to set this equal to 0. So 3x squared plus 6x minus 9 equals 0. And we're definitely going to have some factoring. I see a 3 in all of them. So let's take that 3 out to make the numbers easier to work with. The x squared plus 2x minus 3. Now it's just a little easier. It doesn't have an x with what we took out, so we don't have a 0 as one of our factors because it's just 3. But we're going to then factor what's left. So what multiplies to -3 that adds to 2? Well, we know this would have to be x, this would have to be x. And if we look at -3, it would have to be 3 times 1. And we would like this one to be negative to get a positive in the middle. So we're going to have plus 3 minus 1. Okay, so that's going to give me critical values of -3 and 1. I'm going to check my values. So any way you want to do this, we can do x, f of x, or y. You could call that y. And then we need to check -3. We need to check 1. What else do we have to check? The endpoints, -6 and 4. So you have to check all these ones here. So then we're going to put these into which equation to get out where the original graph is? Oh, that was a good hint. We have to put it into the original function, right? In order to get it out, to get out what we want. Okay, so we're going to take -3 to the third and plus 3 times -3 squared minus 9 times -3 minus 7. Okay, so I'm going to put that in my calculator, and I'm going to have -3. You have to use your parentheses, plus 3, parenthesis, -3, or it won't calculate it right for you. Minus 9 times -3 minus 7 is 20. Okay, so that one's at 20. So let's do the same thing for 1. I'm going to hit second-hand enter. I'm going to go up and say, okay, I want this to be a 1 and this to be a 1, and then I'm deleting off the other number, and this negative can't be there, and that needs to be a 1. Oops, I think I put a 0 instead of a 1, because we want 9 times, not that we even need it, but we got to have it correct. There we go. I got -12. So when we put in 1, we got -12. Okay, and then we're going to do the same thing for 6, -6. And I got -61 and 69. Hopefully I did those correctly. So now we have to look, which number is the highest on the y's? 69. So this is our absolute max. Okay, which one's the lowest? negative 61. So this is our absolute minimum. Okay, and every time I go to show this on Desmos, it doesn't come through real well. Usually it locks up my whole system, and then yeah, it's real cool. It's been real cool. We'll see if it works this time. Maybe. Don't mind all my burns everywhere too. Splash a little grease cooking. Yeah, see, it's just, I don't think the graphing calculator is going to come up. I'm just not even going to try. I'm already done. My computer's really struggling. I might just buy myself a new one instead of use the schools. Okay, so